In this lecture, we will talk about TLS certificates, which is like one of the most interesting points in the TLS protocol, because it's like it is something that is not only mathematical, but it also has like a sort of real-world feel, and we will see what I mean with that phrase. So in particular, we will start by reviewing asymmetric cryptography and why, by taking only asymmetric cryptography, like it doesn't work as it is. So we needed to add a little extra. Then we will talk about this little extra that we add, which are the concept of certificates, and in particular a specific format, which is the X.509. And we will talk how those certificates are used in the web of today, which is called the public key infrastructure. And then I will see two examples, two laboratories. In the first one, we will set up an HTTPS server. So we will put HTTPS over a typical web server to protect the communications. And then we will see something that Bianchi asked me to look into, which are called the TLS exporters. And essentially, they are a mechanism which allows to use the master secret share in the TLS connection to generate secrets to the application layer. So you have an application, the application uses TLS to communicate securely, and you can use, it's like you can reuse in a way the master secret so that you don't have to worry, you application developer, about dealing with generating a secret securely. You can use the things already done in TLS. So let's start with the limitations of asymmetric cryptography. So we saw that the cool thing about asymmetric cryptography is that it allows two entities to share a common secret, even if those entities have never communicated before and they don't have a secure communication channel. So anytime you can communicate with anyone securely thanks to asymmetric cryptography. So we have like a channel, we have two parties that want to communicate, and the channel doesn't have to be secure. It can be unsecure, meaning that anyone can look into that channel. And asymmetric cryptography allows you to share a secret in that kind of channel. Now, there are various algorithms to do this. Like I think that we saw in the lectures, you saw the Diffie-Hellman key exchange and the RSA key exchange, Diffie-Hellman and RSA. So for example, in Diffie-Hellman, each parties generate a random number. So like here, the left one generates like X, which is a random value. The left party generates Y. Then they both have like a public parameters, which are the generator and the prime P of the group. And they send to the internet, they send to the unsecure channel, not the secret X, but the protected secret, which is G to the X mod P. So they send this. And thanks to like the properties of this kind of system, an attacker cannot go back, cannot compute the X from the G to the X. And this is essentially what allows it to work, the system to work. And the secret share is G to the X times Y mod P. And even if an attacker gets in the middle and starts to listen, he's not going to be able to recover the shared secret. This is Diffie-Hellman, and this is RSA. Now with RSA, first you ask the public key of like the other, the individual you want to communicate with. He sends his public key, and then you encrypt your secret using the public key of like the receiver. Now, this kind of works out mathematically. I mean, one can see like you can assume that if you cannot solve the discrete logarithmic problem or the factorization, whatever problem like your system is based on, if you cannot solve that, you cannot break the system itself. Meaning, like, for example, here, mathematically, you can, let's say, you can argue that you cannot go from this thing to the secret key unless you know how to factorize n, which you assume it is hard to do. So this is the idea. But here there's a big problem, which at first it's not really that obvious, but it's really, really huge. And the thing is that, and this is like the difference between, okay, in theory it works, but in practice, how can I like break it? What are the limitations of this system? And typically there is a big difference between theoretical results and then practical things that you can actually use in every day to protect your communications. And the problem is the fact that the public key is never authenticated. What you send is never authenticated, meaning that you don't know who sent you that kind of number or that kind of G to the X or G to the Y. You don't have authentication. Authentication is not granted from this kind of scheme. And this is because you know, like the binding between the private key and the public key is a mathematical bound, meaning that it follows mathematical rules, formal rules that you can prove. But the binding between the public key and the owner of that public key is not mathematical. It has nothing to do with mathematics. It is something that belongs to the real world. And this means that the fact that you bind the private and public key, there's this binding. This is not enough in specific cases of man-in-the-middle attacks. So what it means that suppose that you have, for example, this is Diffie-Hellman in man-in-the-middle. So you have an attacker who was able to put himself in a man-in-the-middle position, meaning that he can control the traffic that he receives from one end and he can send it to the other end. So he can tamper with the packets. So like this guy on the left assumes that he's communicating directly with the destination on the right. So he just sends this G to the X mod P as before. So for him, nothing changes. And the same applies for the other party. Nothing changes. But now we have an attacker which sits in the middle. He produces his own parameter of Diffie-Hellman. And then what he does is, okay, he takes this thing and he like remembers that that guy sends G to the X, and he sends back G to the Z, G to the Z, not G to the Y, meaning that here he's sending back something that did not send the proper destination, but he put himself in the middle. And this message, like this thing, is not authenticated, so he doesn't know who sent me this. Is this like safe? Can I use this? So this is like the problem. And he can do this for on the left and on the right, meaning that he can have two shared secrets, and then he can like decrypt one stuff and then encrypt it with the other so that the other reads it properly. So this is for the Diffie-Hellman. For RSA, it's the same thing, meaning that he generates, like we have a secret and we have like two public keys, so the one of the attacker and the one of the original, the proper destination. So when he sends this public key and he gets back this public key, this E2 and 2, this guy doesn't know, is this the proper public key or is that an attacker constructed public key? Because like when he encrypts this stuff with this public key, mathematically we know, okay, we have encrypted with this public key, only the owner of the private key associated to that public key can decrypt. But who is this owner? That's the problem we are left with. We don't know the owner of these kind of things. So like to overcome this kind of problem, we need to add an extra bit to the cryptographic things that we've seen. In particular, we need the concept of a cryptographic certificate. And so here we enter in the words of certificates. So just to do a little recap, the problem is that public key is not authenticated. Whenever I do asymmetric cryptography, I'm using the public key of someone else. And the thing is, who is this someone else? Who owns the private key of that I'm receiving, that I'm using? So like, for example, when you connect to a server, the server sends you the public key, but do you know if it's really the public key of the server or of someone in the middle? And you resolve this with certificates. So the idea of certificate is that certificates allow you to create a binding between a set of keys and an identifier. And the thing to understand is that the public and private key are mathematical concepts. They are like numbers, they are like algebraic objects, they are on the mathematics end of the spectrum. The entity identifier is about the real world. It doesn't have like a mathematical nature. It could be like a string saying your name, an identifier. And certificate allow us to create this binding. And this binding, of course, must be created in a way that it cannot be forged by malicious attackers. So, I mean, this is the idea. You have mathematics on the left, bunch of numbers. By themselves, they are cool, but they like what binds those numbers, like let's say to the site of a bank? I need to know that those numbers belong to that bank and not to a malicious attacker. Otherwise, all the security I can imagine is completely useless. This is why it's really critical, this concept of certificates. So for example, in RSA, what do we have? We have that the binding between the private key and the public key is, okay, the public key are two numbers. The private key is a single number, and they are correlated, they are linked through this modular equation, that the private key is the inverse of the exponent t modulus phi of n. This is completely mathematical. On the other hand, this is, we have already seen the previous lecture, this on the left. So this is okay. You can study this. You can like understand it, whatever. You can prove theorems about it. But the crucial aspect is this other one. How do we know that this public key, this E and N, belongs to an entity identifier? And for example, in the context of HTTPS, which is a context of TLS, entity identifiers are pretty much domain names, because each server has a domain name, like the name which is resolved through the DNS protocol. You want to connect to Google, you write Google on your browser, and this is the identifier. So you want to connect this identifier to this public key. So you want to do this other connection. And this thing is much harder, actually, because it means that this kind of thing cannot be like granted only through mathematics. There has to be a social system that like you can trust to know that this number belongs to Google. So this is why it's really hard, because it's not only mathematics. Like mathematics seems hard, but actually the social aspects are much harder, because we are like humans and things like that. So this binding is obtained using a digital certificate. And I mean, as I said, the idea is that the binding between private and public is done through mathematics, between public and entity identifier is done through certificates. And in the real world, this is implemented through code. So for example, if your mathematics is perfectly well, but the code that checks the like certificate is wrong, you know, you are not good, let's say. It's very bad. Okay, what is a certificate? So a certificate creates a binding, but what is it made of? What is a certificate? A certificate is just a sequence of bytes. I mean, everything is just a sequence of bytes, but in particular, those bytes have a bunch of informations, such as they contain a public key, because of course they have to bind a public key to an identifier, so they must contain a public key. And the format of the public key depends on the scheme that you use. If you use RSA, it's going to be like two numbers, E and N. If you use Diffie-Hellman, it's going to be the generator and the prime. So like depending on the scheme. And then, of course, some information regarding the entity associated with the public key, the binding, the things that are binded. So these are like two fundamental things that must be in a certificate. Public key and entity associated to that public key, which in the example before was like a number and google.com, for example. Of course, this is not enough, because then we have signature, and this is where the binding is created. This is like a contract, and the signature is used to check if the binding is correct or not. It is a contract that has to be signed, and the signature does that. And then there are also like some information about, okay, but what this certificate, how can it be used? Because there are like various types of certificates with various types of uses. And so you have a correct binding, but also there are like extra information regarding, okay, but how can I use? What is the validity? For example, there is also information about the start date from which the certificate is valid and the end date after which the certificate is expired. It is like a contract, like, you know, like an affitto. So, and then some information regarding the way certificate should be used. So like here I said the point after. So how it should be used, and also like, okay, I have a signature, but who is that signed the certificate? Who is telling me that the certificate is valid? And this is important, because I have like public key, entity, signature, but also information about who signed that certificate. So like every time you see a certificate, these things are like key points. You have public key entity, then you have like here I call the CA, which is going to be certificate authority. We will see that later. So we have like an identifier for the certificate authority that has signed the certificate. So there's to be a CIA entity and a CIA signature. And then there's going to be some information about how to use those certificates. And certificate authorities, of course, will play a key role in the distribution of certificates, as we will see. Now, of course, saying a bunch of bytes they contain this information is very abstract. In the concrete, in the real world, there's been a standard which is called the X.509, which is defined in the RFC 5280. And you can like read this standard is very big, very messy, but you can get all the details about the certificate. And another point of complexity of the TLS protocol are exactly these certificates, because they're very complex. So for example, just to make things a bit simpler, these are like few fields, the most important. You have like a version field, which represents the version of the protocol used in the certificate, like a serial number, which uniquely identifies the certificate among all the possible certificates. Then you have the issuer, which is like that CA identifier. It's like who issued this certificate, who signed this certificate. Then you have the validity, which is like, okay, what's the period on which it is valid? You have the subject, which is the entity associated to the public key contained in the certificate. You have the public key. So the certificate creates a binding between those two entities. And then you have the signature. Like actually you have the signature algorithm, and then you have the signature, which here I forgot, which is like the final signature given by the issuer to make the system work.
Can you repeat what the subject was?
So the subject is that entity identifier I said at the start, like google.com, which is the main things that the certificate is for. Like the certificate states the public key is of this subject, and it was issued by this issuer using a specific signature algorithm, and then you have the signature. So, I mean, this is like a lot of complex steps, but they are all put together. So every time you connect to a website, every time you connect to Delphi, you are getting the certificate of Delphi and a bunch of other things. And actually, you're not getting one certificate. You're getting a chain of certificates, so more than one. And we will see why one is not enough, why typically there are more. And like if you have an OpenSSL downloaded, even if you don't, I mean, like you can play around and start to download certificates of web server, because when you connect with a web server, you don't see the certificate. You just like, if I go to Delphi, I mean, the browser does it automatically. I mean, this kind of lock is because the browser code downloaded the certificate and checked that it was valid. If it was not valid, he would say like, warning, this connection might not be secure, reason certificate invalid. Or maybe because it was like expired. And then here you can have a bunch of like informations, like, but I think a better view is like using the OpenSSL command. It's like this one. Like OpenSSL is like very complex software, because like the commands, they are not at all intuitive. So you have to kind of like just check online. You don't have to remember it. But like here in this example, I think that, so here I'm connecting to a website. So I could say like Delphi Uniroma2.it. I give it the port, which is the 443. And then I like give the flag show source, and I parse it with the like OpenSSL parser. So if I do this, and then I do this command, and here I get this bunch of, this is like bunch of bytes. It's not like readable, human readable, because it follows a certain format, which is called the PEM format, PEM. But of course, then one can open this and gets all the different fields. But this is the way they go to the network. So if you like see a connection, you will see those. This is like a sort of kind of base 64 in a way, not exactly, but sort of like that. So like there are various formats. Depending on which you download, you have to, of course, manage it accordingly. So this was the one I showed. And then once you have this kind of certificate, you can read it like better. So I can do this command linked with the other. So previously I did that. Now I'm gonna do this. Wonder if do this if it works. Okay, yes. Now I've, let's say, open it, and now I get like readable data because I have like the version, the serial number, the issuer. This is the signature algorithm. It says like easy DSA, which means like elliptic curve DSA with like an hash function. Here is the issuer, which is like who signed the certificate, which is like it's the Bean to Bu SCCA, so it is a certificate authority. I don't know exactly which is, but this is the validity. So it says like, okay, not before the 5th of June. So like before that, it's not valid, and not after the 5th of June of 2023. So like in 1 year, it expires and a new one has to be granted. Then you have the subject, which is the site that you want to authenticate, that you want to certificate. Here is called like, here you can see Delphi, it's written like on a new line, but the CN here starts with DE, and then delphi.uniroma2.it, which is the domain name of the website. Then you have like information about the public key of the server. You see that it is like, here it says PC public key, so it is an elliptic curve. So I don't think you did elliptic curve cryptography, but it's like RSA or diffie-Hellman, just a different mathematical structure for doing public cryptography. Then you have a bunch of extensions. As I said, this is very complex, but we don't care about those. It's just the idea to get familiar with. And then you have like when it was signed, the signature, the signed certificate timestamp, signature algorithm, which is DSI with SHA, and then I think that this is like the signature itself. For example, an extension is, okay, I am valid for delphi.uniroma2.it, but also for www.delphi.uniroma2.it. So you can add more like names that they are all valid for the same certificate. I mean, this is the thing you see everywhere. If you connect to something and you get like here a black, like a red thing, it's most likely that the certificate has not been properly configured or accepted by the browser. And so here we see all the things that I've already shown, like the serial number, the issuer. In this case, it was from like my website, but it's the same thing. I mean, I use RSA. So like RSA with 2048 bit. And the exponent, I mean, this is like the modulus, this is the n value, and this is the e value. And so this is my public key, the public key of my server, e, n, and e and n. Then a bunch of extensions, and a bunch of extension, yes. The signature, which was also signed with RSA. And so like this is, I show the OpenSSL command. There is also like this library, which is pyOpenSSL, and it's cool because it is like a Python interface to the OpenSSL library, meaning that you can use Python to establish SSL TLS connection, to maybe get information about certificate, to do a bunch of things. It is not like you cannot do everything, but you can do the most important things. And here I show like an example which maybe you want an application to simply download the certificate in a JSON format, because then you can do like automatic things. You can do like maybe you can be alerted when certificates expire. I don't know, whatever. So like in this function creates an SSL connection, you give it a DOS name, like for example, a string, Delphi, blah, blah, blah. You give it a port. By default, it's 443. And then you say, okay, you encode the destination in a tuple in Python, host port. And then you create a socket, a basis socket. And then you create a OpenSSL context. Like, of course, this can be configured. Here, I think I put one of the lowest protocol simply because my objective was not to like communicate securely, but was to accept the certificate of the server. So even if the server offered a low version of SSL, like SSL v3, I would still accept it because I'm only interested in the certificate. Otherwise, it would crash because it was like, the version is not enough, but I don't care about that. So you create a context, then you create a connection, and then like you set some stuff in the connection before actually performing the handshake, and then you perform the handshake with the function do handshake. So like all sorts of libraries that work with TLS have the same structure, which is first you set up a TCP socket, and then you wrap the TCP socket with like an OpenSSL, like an SSL TLS kind of object or like a function, depending on the library. So here, this is where I wrap the connection. I put the socket and the SSL context, and I get a new socket, which now is an SSL socket. Now I can communicate securely. And then I return the new socket, the newly created socket. And then here, for example, I get, okay, I have an SSL session, which is a socket. I get the server name, which is like google.com, and I put it in my like dictionary to get the certificate. And then I put the version name in the TLS version field of my dictionary. And then here I use the function get peer chart chain, which uses the TLS connection that has been created and extracts the certificate that has been used to validate the session. And so here I have to enumerate them because they could be more than one. It's more than one certificate. And for each certificate, I put the ID, which is like 1, 2, 3, depending on whichever many. And then I do dump cert data. I extract only the data that I require for my application. And here in the dump cert data, which is the longest, I simply extract a bunch of fields just to show how you could interact with it. I mean, it's just like teaching example. Here I get the common name of the subject field of the certificate. Like all the fields, you can access them through Python. For example, the public key, I get like, I have an if because if it is like elliptic curve, then I have a certain structure, otherwise I have a different structure. So like things like that. And then I return the cert data, and you can, this is how you use it. I mean, go here, and to like the requirements in terms of libraries, they are simply like the pyOpenSSL pretty much. So here I'm gonna create like an environment, virtual environment to download all the required packages. Then I'm gonna activate it. I'm gonna install all the dependencies with pip and the requirements file. All of this, of course, in the lecture material. Now, pyOpenSSL by default, it's not enough because you still need to have installed OpenSSL on your system because it's just a wrapper. It simply calls OpenSSL. I have already installed. And then once I have everything installed, I can simply go here and I can do like, I can call the example1 TLS cert. You can ask me, okay, to use me, you have to do like host and port. I can do like Delphi, uniroman2.it 443. I get like a small viewing of only the data required, maybe. And I mean, this could be cool if you want to maybe check, okay, what is the actual security of the web server I connect to? Like, if you have a weak public key, I mean, the server is done. You can just break it and go on. Typically, there are automatic means of protecting servers, so this is rare to find, but you could find it if it's something like badly maintained. Like the fact that the certificate expires in 1 year means that like you have to be careful on those dates where the certificate is expired, because in those dates it is vulnerable. So like this is just to to get familiar with these things. And even if like certificates have a lot of fields, what you need to like get a handle are just a few actually. The rest is more like for other things in more complex time. So, but these kind of certificates, they have to like by themselves, they have to be managed in a specific way. And this is where the public key infrastructure comes in, which is all the infrastructure that arises to use those certificates. Like for example, I said, if we check like this thing, it says, okay, the issuer, like here we have two certificates. We have a certificate of type 0 and a certificate of type 1. So the thing is that this is the certificate that binds Delphi to a public key. And then it says, look, the issuer is this one, is this guy, Giant or V, whatever, this certificate authority. And then I have the certificate which binds this certificate authority to this public key. And then I have another issuer. So it is like a chain of issuers, like, okay, this thing was signed by that guy was signed by that other guy. And so like, how do you validate this? Because now, okay, now we have this object. It says it was signed by this certificate authority, but who grants like this concept of authority? How is it managed? Because it's very important. Like maybe an attacker could be this one and nothing has changed. So we are introducing complexity, but now we have to understand how is it managed, because otherwise it's completely useless. And this is where the concept of infrastructure comes in. Because once again, public key is not enough. Certificates, okay, but certificates have to be managed. And there is a complex infrastructure that is used to manage those certificates. Like here in this like diagram, which are taken from Wikipedia, we can see three main entities, which are called like the array, CA, and VA. So, I mean, like array, I think it was like, I don't remember well, but it was like, it is the entity that grants the certificate. It's like, it's the entity that checks, okay, you are the bank. So this association, you are the bank and you have this public key. So this association is valid. So it's like the things that validates this kind of things. Then you have the certificate authority, which actually generates the certificate after the check has been done. You know, after maybe I go to the bank, I check the server, whatever, and I say, okay, these are trustable. Okay, I generate a certificate. And then like you have this like validation authority, which is used during essentially like your browser. When it validates a certificate, it's doing like a validation. It's like checking that the certificate is valid. So like with PKI, public infrastructure, it is we compose the set of protocols, policies, and all the mechanism, cryptographic mechanism, that drive the management of public key certificates. So in the context of the SSL TLS protocol, the PKI is used to authenticate the server and client. So all the stuff about TLS, the fact that it grants confidentiality, integrity, authentication, and a bunch of other things, right? Okay, confidentiality, integrity, and other things, they are done by the TLS protocol, but they assume that the authentication step was correctly performed. And the authentication step is not only the thing of the TLS protocol. It is TLS plus PKI. So it is an external system which sits outside the protocol. And it's crucial because if that external system is weak, the protocol is also weak. So to understand the concept of PKI, we need to review trust. What does it mean to trust in the context of certificates? Certificate authorities, the hierarchy of the PKI, and now they are used in SSL TLS. So let's start with probably the, I guess, most complex topic, which is that of trust. Because we said that certificates bind the public key to identities. And then, okay, I have this binding, but this binding doesn't have mathematical value. It's meaningless mathematically. It's only meaningful to us, clients, servers, who wants to communicate securely. So the question is, what is it that makes a certificate valid? And essentially, the idea is mainly, it's not only this field, but it is mainly the signature, like who signed the certificate. You have to think it also in terms of like euros. I can like take a bunch of paper and I write 5. That is not 5 euros because they were not signed by the Central Bank of Europe. This is the same thing applies for certificate. I can write a certificate in which I tell to have the public key of Google or like that I am Google and I have this public key, but it's not like valid by itself. The signature has to be made by someone particular, by someone special. And what do we mean by someone particular? By someone special, we have to talk about trust. And you know, what does it mean to trust something? It's hard. I mean, why do we trust the Central European Bank? It's hard to say explicitly why, but it's mainly because it is a system that already exists. And like in a personal relationship, trust is very, very hard to define properly. But of course, we are not talking about personal relationship. We are talking about technical context. So the way we're gonna define trust is gonna be way more specific. So it's like way more narrow, very, very specific things. So in the context of the PKI, we trust a certificate only if we acknowledge the entity that has signed the certificate. Okay, what does it mean? We acknowledge. How do we do this acknowledgement? And the idea is that we use an internal database. So we use this database, which is called a trust store, because it stores something related to trust. And when things are saved in this database, we trust them. It's like we have a personal vault. Each one of us in our computers has a personal vault. If something is in there, we trust it. If something is not in there, we do not trust it immediately. So as I said, very specific things. It's in the store, we trust it. It's not, we don't. Very easy. So in particular, in this trust store, we find specific certificates, which are called root certificates. So they are the same as the one I showed you, but they are called root because they are in the trust store. And what's the idea? We trust the root certificates directly because they are saved in our store. But also we go a step further and we say, okay, we trust the root certificates directly, and also we trust anything that has been signed using a private key related to a public key contained in a root certificate. So this like a bunch of words. To recap, let's say that I have certificate C1. I ask myself, do I trust this certificate? I pose one question. And the first question is it in the trust store? If it's in the trust store, if it is, then I trust it. If it is not in the trust store, I don't immediately like dismiss it. I ask, okay, maybe I don't have it directly on the trust store, but maybe on the trust store, I find another certificate, C2, and essentially I bind C1 to C2. I create this, I check essentially that C1 has been signed, the signature has been done by an entity that was certified by C2, by an entity that I have that I trust because it's in my trust store. And so this acknowledgement can be done either directly, I have it in my trust store, or through a chain of certificates. And this is why the concept of chain comes in. I trust it directly or by going through various steps. But at the end, all those steps, they have to end always with, okay, something is saved in my database. And now we can talk about certificate authorities. So, I mean, here the concept of trust is tricky, but it is also easy. I have it saved, good. I don't have it saved, maybe I can go like one step in the chain and I have saved something one step further. So like certificate authorities are the entities whose job is to store, sign, and issue digital certificates, such as the one used by TLS, which are the X.509 certificates. So, I mean, as I said, with the trust store, we store the root certificates of trusted certificate authorities. So, a certificate authority has to be trusted. And it is trusted only if it is saved in our trust store. And the idea is to trust anything that is signed by a trusted CA. It's like trust flows like, you know, down in a way that, okay, I trust a big certificate here. These certificates signs a bunch of other certificates, and I trust them because I trust the one who signed them. And it is, we will see how it is organized. But essentially, it is organized in an hierarchical structure where the various certificates authorities have like layers. Like there can be top level, which are the root. The root are like the most powerful. Like, I don't know, the Google certificate authority, you sign something with that, it's good like everywhere. It's really powerful. There are also like mid-tier certificate authorities that sometimes they work, like sometimes they are accepted, sometimes not. So like depending on the chain, depending on where you are, there could be like certificate authority at the top, layer 0 or layer 1, or like something like that. And at the end, you have like certificate. So you have a different kind of structure. And of course, if you sign something with this, like you are super powerful. And of course, the more you go up, and the more these kind of things are like managed really, really like securely, because otherwise you could break like the internet. So that's dangerous. Now, the role of each certificate authority is to issue certificates. Of course, they have to issue them only to the valid entities, only to the correct entities. And this can be done by introducing like other components, like an array registration authority. I mean, here the things can be really complex, so we don't have to like delve into the specific details, because this depends a lot on like the way that you want your system to work. Like this is like a simple scheme. It could be very, very complex. It also depends on the bureaucracy of the like country you're in, or like on the system that you're using. So like it could be really hard, but the idea is you issue certificates only, of course, to the entities that have somehow passed other checks. Otherwise, it's completely useless. So this is the idea. And to generate a new certificate, you have to create a so-called certificate signing request. So like you create a request, the request has to be, of course, validated, like it has to be a valid request. And so what do you do? When you want a new certificate, for example, you are creating a new website for yourself. You want a new certificate because you want to protect your traffic. The first thing to do is you need to get a hold of a certification authority that is trusted by others. So the process of generating a new certificate is, first, you generate a public and private key for your server. And you store the private key, and you, of course, publicize the public one. Then you create a new certificate request. And this request, of course, says, look, I am shop.com. I have this public key. I want to certificate that I am the owner of this website with this public key. This request is sent to the PKI system, depending on whichever you want to participate. It is validated, and after the authenticity has been checked by like someone else, an external system, you get back the certificate, the signed certificate by that particular certification authority, and to each client, you use that certificate. Of course, this means that depends on where you send these things. I mean, if you send this certificate to like your certificate authority of like a small place that no one cares, that certificate, no one cares, you know, it's like useless. So this is the social aspect. And this is also the things that makes it hard, because you want to protect your traffic, but at the same time, to protect your traffic, you need to validate your website, your company, whatever, to a certificate authority which is very recognized among all the other clients.
Shouldn't everyone like use Google at this point?
Yeah, but like I'm not sure if Google has a certificate or authority. Like for example, for my site, I use Let's Encrypt because it is a non-profit, and so how do they do it? Like if like in the like when you go to the teaching, this thing is TLS protected because I have asked Let's Encrypt to sign my certificate. Now, when I asked Let's Encrypt to sign my certificate, what do? They check if I'm the owner of this domain name. And to check if I'm the owner of this domain name, they like, there is a script which is called TLS chart, I think. No, chartbot. Chartbot is tool to obtain, so it's actually automatic. I didn't do anything. It automatically did it. But essentially, you launch this script on your server. This script communicates with the Let's Encrypt servers to like do like a challenge request. Like they say, okay, if you are the owner, put this in your website, because only the owner will be like put a special resource on a specific location on the website. So they check if you have actually if you control the content. And the moment you control the content, they generate a certificate. And the cool thing about Let's Encrypt is that the certificates which are generated by Let's Encrypt are like validated by each browser, because each browser, Chromium, Firefox, etc., they have in the trust store a root certificate of Let's Encrypt. Because otherwise, it's like if I do the previous script, like
So there is no point in using like anything else, choosing trust store of every browser.
I mean, you can, but no one will connect to you because they will receive the, like, there is here, there is also an economical, let's say, things to consider, that the developer of browsers, they want to ensure secure communications. Otherwise, who is going to use that browser? But to ensure secure communication, they have to put heavy, like, pressure on like this kind of certificate authorities. Because if you have a bad certificate authority, for example, if Let's Encrypt did not check that I was the owner of my website, I could generate a certificate for like, I don't know, like google.com. Now, this kind of attack, if I put myself, for example, in the same Wi-Fi here, and I started to domain in the middle, and I put a google.com website which is like similar to the official one, I also have a certificate which certifies that I have the domain google.com. I can, of course, do phishing attacks. So browsers have to make sure that certificate authorities, like that, the authorities they put in the trust store are actually trustworthy. And this is very expensive as like things to do. So there is Let's Encrypt. There are also other services. Like, for example, sometimes you pay for the domain name and you get a certification authority for free because you paid otherwise. Let's Encrypt is, for example, completely free. Other certificate authorities you have to pay. So it depends. It's like a business. It becomes like a business oriented depending on the kind of signature you want. And all of this discussion regarding TLS certificates also applies, for example, to code, which are like code certificates, meaning that you certify your code to run. It's nothing to do with TLS, but it's another kind of things. It's similar. And also for that, you have to pay. So it depends. So Let's Encrypt is cool because it's free.
You make also pack with Let's Encrypt.
Can you also?
Of electronic.
I think I'm not sure. I've never used it, but yeah, I never use it. Yeah, not sure, but yeah, has to be checked. So this brings us to this concept of hierarchy, because we said that we don't download just a single certificate, but a chain of certificate. Like here in my website, I have a chain of 3 certificates. I have 2, 1, and 0. So 0 is like the certificate which is going to be used in the handshake. But to validate this thing, it's like a leaf. To validate the leaf, you need to go up, and you need to go to, okay, who issued this one? R3. Okay, R3 has this other certificate. Who issued this one is ISGR root X1. Okay, who issued this one? DST root CIA X3. And probably this DST root CIA X3 is saved in the trust store of Chromium. So this is good. I mean, I'm not sure, I don't remember exactly where it is, but for example, if you want to, we will see later, but certificates, security, gestisci certificati, manage certificates, and here you have essentially the authorities, authorities. Here are all like the authorities that the browser acknowledges, let's say, and you can like check per visualizza. You can check all the certificates of these kind of things. So this, like everything that is signed by those guys, either directly or indirectly, it gets validated. And so like we have to download a chain of certificate. And here comes, of course, the concept of hierarchy, because we have different kind of certificates. We have leaf, we have intermediate CAs, and we have root CAs. So like leaf are like certificates which are used to identify actual websites, like my website, Delphi websites. So like they are the final one that are actually used in the TLS handshake to extract the public key and all the rest. And the remaining are used to manage all the leaves, which are the intermediate and the root. For example, I could have like a root CA, which signs two intermediate CA certificates, these others, and those intermediate with less power. So every time you go down, maybe you have less power. Maybe, for example, the root can sign any sort of domain. I don't know, the intermediate maybe can sign a subset of the domains, or it can only sign like specific things. Like the root is powerful, all the remaining are more constrained, and they have to do to like it's not really decentralization, but to distribute the load so that you can instead of having a single server, you can have many different authorities. For example, Let's Encrypt is used all over the world, so to have only a single authority will be like hard to manage. But at the end of the day, the idea is that from the leaf, we have to go to a root, and we only trust if it's saved in the trust store. So this is like an example of a two-level chain. This is like the final certificate, the leaf one, the one that says, for example, that Delphi has a certain public key. This one was signed by an intermediate CA, and this one was signed by a root CA. So to check, the process of checking a chain of certificate goes through, okay, here I have to check that this thing was signed using the key of this other certificate. And what's the idea here is that in this certificate, I have a public key. For example, I have EN. And here I have a signature. So we go back to like the concept of RSA signatures. This signature was computed using, for example, M to the D mod N, using the private key of this intermediate CA. So only that intermediate CA could have computed that signature because it required the knowledge of the private key. But then once I have the signature, I can check the signature using the public key. And the public key is certified in the next certificate. So a little bit confusing, but then you get used to it. It is like all the information you need at the end. So all of this you can check mathematically. At the end, you cannot check anymore because they are so called. We said that like this certificate is signed by this other entity. This certificate is signed by these other entities. Okay, but this certificate, who signs the root certificate? No one, because otherwise we would keep going. And so the idea is that this is a so-called self-signed. It's like I create a certificate and assign it with my key. So it's like it's kind of cheating, I guess, but it works because only the root ones are stored in the trust DB. So like for everyone else, the concept is this is valid if it was signed by the one before. For the root, this is valid if it is saved in the trust DB. If I create a self-signed certificate, and we will do at the end, it's not going to be valid for Chromium or for Firefox or for whatever, because it was self-signed and it was not stored in the database. And so that's right. Every time you download Chromium, every time you download a browser, each browser has a list of valid root certificates, which changes, of course, depending on the release.
So if root C is trustable, why we have safety transparency database?
Yeah, the other aspect is it has to do with like even like what I discussed here. Actually, also this has problems, and it becomes more complex because, for example, what about if a valid root certificate is compromised? So I have a valid root certificate, my server gets attacked, and the attacker gets hold of the private key. He starts to sign everything. So now there needs to be mechanism to like revoke certificates or to understand if a certificate even my database could be corrupted. And so like, I'm not going to talk about this in this lecture, but essentially the idea is that this is not the full picture. This gets to the full picture, but like the full picture is complex. And the missing aspects are that you need a way, a more complex, a more sophisticated way to understand if a root certificate is valid, because one, root certificates could be like leaked to attackers. So you need a revocation mechanism. So you need revocation mechanism, meaning a mechanism that tells you, okay, technically this thing is valid, it's stored in my trust DB, but it has been revoked, especially because it has been attacked. So this is an aspect. And the other aspect is that like I think that with the transparency, I'm not completely like sure, but with transparency, the idea is to have like a distributed way of checking these kind of things, so that the knowledge that you have, like, look, I realized that this certificate is now compromised, you can quickly spread to others. And so you have like a view of the status of the certificates, which is like is sort of like trustable in a deeper sense than simply the database. Because as we said, if I only trust, for example, my database, if someone malicious gets to my database, once again, I am attacked. So the idea with transparency is to have like a publicly available like a list of certificates which you can which you can modify or which you can check, that tells you, okay, this is valid, this is not valid. But that is more complex, and it's like a different this is a subtopic which in itself is a bit complex. But yeah, this is a good question, because all of this is not the full picture. Like this kind of certificates, the complex part is that it's not only technical, it's also social. And about like transparency, there was also a thing, I think that maybe Bianchi will mention it, or I don't know if he already has, about like even if you have a server that tells you this information, how can you like of having something that is reliable to like even nation state attacks? Because if you control a lot of servers, then you might have the wrong picture. You might so it's kind of complex for that, because certificates are probably the most weak part of TLS. All the rest is cryptographically strong. You can prove all good. This thing is where things break down, let's say. So with certificates chain, you have that the issuer of each certificate matches the subject of the next, and there's that what I mentioned before, that linking of signatures. And the last certificate is the trust anchor, which for now we say has to be stored in the trust store. Now, to finish off, before going to the laboratories, how are they used in TLS? Now, TLS allows you two kinds of authentication, server authentication and client authentication. So server is the most typical. You connect to the server and you authenticate the server, but also client is allowed, meaning that the server authenticates the client. So here it was like an handshake of TLS 1.2. And essentially, how it works is that the first message is from the client, which says the client hello. Then you have the server hello, and after the server hello, the server sends its chain of certificates. So this is like the third message. After that, the server sends its public key. And after that, the server sends its server hello done. So it means that the server key exchange message, which contains the public key, is authenticated by the previous one, which contains the certificate. Of course, the client, when he received the server certificates, he starts to do that checking of before, and he's like, okay, can I arrive at a trust anchor? Can I arrive at a trust certificate? If I can, I'm good, and I accept the server key. If I'm not able to do this kind of authentication, I simply drop the connection, and the rest does not continue. And the format of the server key exchange depends, of course, on the public cryptography used. For example, in RSA, the server generates a key and he encrypts it with this public key. And so in the server key exchange, he sends this thing, key to the E mod N, and in the certificate, it's written, look, E and N belong to google.com. So when the client authenticates the certificates, he also is authenticated in the server. He can use the public key contained in the certificate to extract the message. Actually, here it was protected with this private key D, not E. So it goes, okay, I do K to the D to the E mod N, and I get back my K. So this depends on the public cryptography used. I will not go into the details, but yeah, fundamentally is in the first, like in the second, in the third message, which is the second reply of the server, certificates are exchanged. And this is only server authentication. Client authentication is, we will not see it in this lecture, but it's the same thing, but it works client side. So the client, and it's interesting because when you have, like, for example, an application in which you know, okay, this application will be used by few people, like you are at work, you have like a web development platform that you can access from outside. You do not want to give out passwords. You can give out certificates, like 3-4 certificates to each one of them. And you can say, okay, you have to put them in your browser and you will connect thanks to the certificate. So they allow maybe to have a web app which doesn't require passwords, but it's still valid because an external attacker cannot have a valid certificate. If, of course, they are like managed well by the server. So now we will do like a 5 minutes break, and then we'll see how to set up an HTTP web server and this thing about TLS exporters. But now, yes, so we will start in like an account 5 minutes from now. Okay, so in this like last part of the lecture, we will see two labs, two more practical things. And in particular, I wanted to show how easy it is to set up HTTPS like without using automated tools, like you just do everything by hand. And I think that this shows that it is not really that hard. You just need to know a few commands. In particular, I will show you how to like get a web server, which typically handles only HTTP and adds the TLS support, SSL, whatever. And we will use like Ubuntu with Nginx and OpenSSL. I mean, you don't have to have known Nginx, but it is like a cool HTTP proxy server to use. So I suggest to look into it anyways, because at work you will probably like see it one way or another. So in particular, I have created a Docker image to play around with this thing. You don't need to know Docker. You can just look at me. I mean, this is just demonstration. You don't have to know it, but I think it's useful. And then I can give you the image later if you learn Docker and you want to play with it. But essentially, like like I have to start the actual image. So Docker is like a sort of not really a virtual machine, but it creates like environments inside of the computer which you can interact. Here I'm gonna like SSH into the Docker. I think that the part is this. Okay, so here inside I'm like in a server. You could say like in any server. We don't care that it is a Docker, and I have installed OpenSSL and I have installed Nginx. So these are already installed, but we will see how to install them in case. So the idea is to start from this, and I think that if I do like, first I have to get root. Okay, then I do like, if I do start Nginx, and I simply connect to with my browser. This is like the web server, and it is not HTTP. It is not HTTPS. This is just HTTP. It is not protected. This is the default view. Here I could put anything, but the key point to understand is that with this, nothing is protected. Any kind of fields that I put, like for example, I could put here a password. Anything goes through the network, everyone can see it, not protected at all. And now we will put, let's say, HTTPS. So this is like, the version of Ubuntu, which is the 20.04, the version of the kernel. I mean, we don't care about that, but just to point out the starting point. So we become root. So we have to install Nginx and OpenSSL. We can do that in Ubuntu with these commands. I already have installed them. So like, I don't need to do that. So reinstall. Now, the first thing to do, of course, is that concept of like all the things about certificate that we said. We need to generate one certificate for our server, and we will do a self-signed certificate. So, I mean, we don't care about certification authorities. We will do a self-signed. Chromium will complain to us, of course, because it's not in his trust store, but it's just for demonstration. And in particular, now, as I said, OpenSSL is a mess of a software, specifically with all like the command lines, attributes, and like options and things like that. There is a command which allows you to generate a new key, a new private public key, and also generate a self-signed certificate with the key. So it's like two things in one command. There are also like different commands for doing different things. I mean, here, do not think about remembering these things because it's impossible. Use Google and just understand what you need to do. Essentially, we need to generate a key and a certificate, and we can do this with, first, we request a new X.509 certificate, for example, that is valid for 1 year, 365 days. But also we request that this is going to be it's going to be signed with a new key. It's going to be like, it's going to certify that I am the owner of a new key that will be generated. And it's going to be RSA. And here I put the number of bits, 2048 bits. Then I say, okay, the key you put in this file, which is called Nginx self-signed.key, the certificate in this other file, so that I have both things. Now I execute this command within the Docker. I do this. It's going to ask me a bunch of stuff that they have to put in the certificate, like country name, state. I mean, this is like nonsense. The most important thing is the common name. Now here, if I want a valid certificate, here I should put the domain name of my server. For example, if I am Delphi, I would put Delphi. If I am Leonardo Damiano, I would put Leonardo Damiano. Here we put like localhost. We don't care about this thing. Now we don't care. So I have pressed OK. Email address, we don't care. So the most important thing is common name. And well, else I have these two files, which are this I have this, which is a pen certificate, and I can like this begin certificate, and we can read it with like the old command. I think that maybe I have it here as well. So here I put in Nginx signed. So this is command allows us to read what we have generated. Yes. So this is the thing that we have generated. So we put the version, the validity. It is valid for 1 year, 6 December today, 2022 until 2023. The issuer is localhost and the subject is localhost, self-signed. Issuer is equal to the subject. Here is the public key, the modulus and the exponent. And here are some extensions, things like that. So correctly, this is the certificate. And then I have my key, the self-user key. So this, of course, I mean, it's private, but this is a demo. You shouldn't, this is private. So this is the RSA private key. And these are like the first two things we need. And the common name of the field, as I said, it has to be equal to the domain name, which is resolved through the DNS protocol. Now, after we have created these two files, we can move them into appropriate directories which are used by Nginx. So we can just say move. Okay. Now we generate the parameters of Diffie-Hellman. These are the public parameter of Diffie-Hellman. And I say like, okay, with OpenSSL I generate them. I say put the resulting file in this directory, etc SSL, and it has to be like 2048 bit. So this is the generator and the prime number of Diffie-Hellman. It takes a bit. Now, of course, this is not done every time. It is done once to configure your system. You can also put like a longer size bit. And this generates in Diffie-Hellman, this is the generator and the public, the prime value, GMP. Of course, this is taking the entropy of the system to generate them, which takes a bit. And probably it also takes a bit because my laptop is a little bit slow. So yeah, this is also a real example that entropy is hard to generate. Or anyways, that cryptography requires performance, you know, it is hard to make things secure and performant at the same time. But I will wait like 10 more seconds and then I will generate like primes of 1024. Because I mean, I tested it on my desktop and it wasn't this low, but yeah, this is also teaching experience. Yeah, I mean, fact is, and we're gonna be weaker. We're gonna be weaker. Okay, you see, this is the big difference. So I have, instead of doing a 2048 bit, I've reduced the bit. It was so much faster, but of course it's also so much weaker. So in this demo, we don't care. But in real life, I mean, as of today, 1024 is still pretty secure. But for example, I think that maybe a nation with resources of a nation, 1024, it's like, I don't know, 2048 is much harder to break. So you have generated the parameters, and the parameters, they are simply another file in like PEM format, begin DH parameter. So once we have the parameters, what we can do is we can, now we can create the configuration file. So here, it's like you cannot see everything because now I will put on the other thing. So this is the main SSL configuration file. So here it contains, for example, the protocol that we want to support. For example, here I'm saying TLS 1.2. I could put 1.3 because we want to be more secure, and 1.3 is the better one. Then we say, for example, okay, the Diffie-Hellman parameters, you take them from this file. Then we say, I want to support all these ciphers. I want to support this elliptic curve. I want to put this kind of headers in the HTTP response of my server. I mean, you can like play around with this, But the main idea is that all of this has to go like inside this kind of file. So here actually I'm going to do this thing. I'm going to do I'm going to use another thing because I need to open the text editor with Nano. I'm just going to copy and paste this file to here, to paste, and I save, and I have this file saved. So now here the path was etc nginx snippet, I think, snippets. So here I have this SSL params. I do cut, and I get the parameters that I've put. Okay, now I need to create the Nginx virtual host configuration file. This is essentially the main file of Nginx. Here also in Nginx, so Nginx essentially works as follow. You put this file in this directory, and you say, look, you listen on the TCP port 80, but I want to wrap that channel with SSL. So TCP wrapped with SSL, you have to say, so this is for IPv4 and this is for IPv6, this weird dot, etc. Here we put the SSL configuration saying, look, I want you, this TLS socket has to provide this certificate with this key and with this configuration. So this is the main idea. So like 3 lines essentially for doing SSL. And the rest is simply the web server configuration. Like for example, the root of the web server has to be in this folder, in the var www.html folder on the file system of the server. And then you can do like a bunch of other things of Nginx. The most important thing is that if you take a default Nginx configuration, you simply add these like SSL here, these 3 things, and you are good with HTTPS. So I'm gonna copy this thing as well. And I'm gonna edit the sites available default. So in the default, you have a lot of comments because it explains you a lot of things, but we just copy this minimal configuration just to show that it works. So we do this, and then we restart the service. So we do service restart here, starting OK. Now, when previously we connected to the site and we already had HTTP, I now go to this website. So wait a sec. The plane was sent to. I have to put HTTPS now because it is a different protocol. Same port. Now I get this message because now I have HTTPS. So now the traffic is encrypted, but the browser tells me, look, the cert authority is invalid because the certificate that I obtained, the certificate that the web browser has obtained, is not valid because it has been signed. Here we can see localhost, the one I put during the creation, and it is a self-signed certificate that doesn't belong to the trust store. So the browser doesn't know how to trust it. Of course, I can say like, okay, but you can like trust me. You can trust it. And now, of course, it says not secure because you have forced the authentication. But from here on, actually, if you check the traffic, every parameter you send is going to be like encrypted, and you can check this with like on the external system, like here. So I can use curl to connect to my web server. By default, it says certificate problem. I can put the parameter K, and it's gonna connect properly. And then I can put the parameter B for telling me the handshake, for detailing all the things that go on with the handshake. And essentially here I have, here in this part, all these TLS handshake, client hello, server hello, certificate, server key exchange. So I get all these messages. And so I can see, for example, that at the end, the connection used TLS v1.2 with this kind of parameters, and server hello. So yeah, so like I'm not sure why it says 1.2 if it's like server side or client side, but whatever. You can see the final version and the supported cipher. Probably because if we check the configuration, if we check the SSL param config, I think that okay, yes, here it was. This is, I forgot to change it when I copied it. So I put 1.3 now. You can see it. I put 1.3. I restart the Nginx. I do restart. I do a curl with curl again. Now it says and shake new session ticket. That now it uses like okay, now oh shit. Now it uses TLS 1.3 because the server supports 1.3. What happened previously was the client wanted a 1.3 connection, the server only supported 1.2, so the client was like, okay, let's do a 1.2 connection. But now the server supports 1.3, and I mean, this is just like an example. I will not go any further, and you can mess around with it, you can change things, etc. I have created a Docker file. You just install Docker, and then you follow these commands. You copy like this Docker file somewhere, you do these commands, and you can run the Docker, and you can like SSH into it and play around. Now I will do real fast, like 5 minutes at most, to talk about exporters because Bianchi told me to. So essentially they are a mechanism for exporting keying material from TLS to an application. So it means that we assume to have established between client and server an SSL communication, like a TLS SSL channel. Now, during this communication, a master secret has been shared from client and server. So like client and server have the same master secret. Now, this RFC defines a mechanism that you can use to take the master secret that is already shared and extract random data from it to use at the application layer. So like if you check the app, you have like client and server with the like TLS, and with this you can extract from the TLS random, pseudo-random numbers, but essentially they are like secrets that you can use for like application sensitive things. Depending, of course, on the application. This mechanism is agnostic to the particular application. And you give it a label string, you give it a length value, and you give it a context, which you can also omit. And essentially, it uses the same construction used internally by TLS, because in TLS, the master secret is not used itself to protect confidentiality, integrity, and other aspects. It is used as a seed to extract all other keys. So I like to think in terms of like, they are sort of, Horcrux. They are sort of fragments of the key. They are created from the key, but you can like do many things. You can create key 1, key 2, key 3, whatever. And this is another mechanism to create another key, which is not used by TLS internally, but which is used by external application. And there are two different ways of using it, without context or with context. And here the PRF is the pseudo-random function, which is the same one used in the TLS session. So if it is like SHA, you use a SHA or otherwise. And for example, in pyOpenSSL, you have this function, export keying material. It's very easy. You establish an SSL like before, exactly like the snippet code of before. And then you do this wrapper, essentially. I mean, I have the code here. So it's example 3. You essentially do this. First you create an SSL session. And you say, okay, I have this SSL session. You use this label exported experimental, which is defined in the standard. You can read it. So you don't even need to like put a label. You can use a default one. You just need to put a length. You can say, okay, I want, for example, like here in this example, I think that I used, so let's go out here, start shell, here I put the environment, the Python environment, env, I activate the environment, and then I do Python 3, example 3. Here it says, okay, give me a host, give me a port, and give me a length. So I say like Delphi, Roma2.it, then I say 443, and then I say, for example, I want 6 random data, and it has generated, if you can see, these 6 bytes, which in X, it's like, these are the 6 bytes. Now, these are generated using the underlying connection. I can also say 120. I can also say whatever, how many. And the cool thing is that I just use the underlying TLS structure, and I know that this data is kind of secure. I mean, the assumption is, if one can break this data, one can break the entire TLS connection. So, I mean, it is like it's like you rely on the TLS. If TLS is broken anyway, you are kind of, so this is the idea, and it was defined in that RFC. So this is it for this lecture. So the most important things, also in the view of future X and whatever, it's like understanding that certificates bind the public keys to entities. And anytime you think about a certificate, you have to think about these 4 things. But also you have to understand that it is not this basic, because there is an entire social infrastructure which relies on like economics. So there are complex things which go outside the technical aspect of cryptography. And all the social structure is to make sure that certificates, the binding in the certificate is correct. So all the social aspects, all these kind of things, all this, even the transparency things, all the initiatives have one goal: to make sure that essentially when you connect to a bank, you know that those numbers are actually those of the bank and not someone else. So this is the media. All the rest is like details, but you need to know these key points. So this is it. Thank you for your time, and I will stop the recording.